Okay, class. Okay, we continue with our part B. Okay, so our subtopics about the flux and the flux density. Okay, so the magnetic flux is represented by a symbol of V, and the unit of the flux is Weber. Okay, so magnetic flux density or V, okay, is the amount of flux per unit area perpendicular to the magnetic fields. Okay, so we know that what is the magnetic field? Magnetic field, okay, is the dot line, okay, that formed, okay, by the magnetic flux. Okay, so its units, okay, is in Tesla, okay, for the flux density. Okay, so magnetic flux, the symbol V, and the units is Weber. Okay, and the magnetic flux density or B is the amount of the flux, okay, per unit area which perpendicular to the magnetic fields. Okay, so its unit is Tesla. Okay, so 1 Tesla equal to 1 Weber per square meter. Okay, so magnetic flux density, okay, the unit is Tesla. Okay, which equal to Weber per meter squared. Okay, so means which is equal to the flux per unit area. Okay, so the B, okay, the flux density is the V divided by the area. Okay, the flux is, I repeat again, the flux is V. Okay, the unit is Weber. While for the magnetic flux density or B, okay, is equivalent to flux, okay, per unit area. Okay, so in example, okay, the flux density in the magnetic field in which the flux in 0.1 meter squared area, okay, is equivalent to 800 microweber. Okay, so using this formula, okay, so you find the flux density. The flux density is B, okay, and then the P or the flux is 800 microweber, and the area is 0.1 meter squared. Okay, so the B is equal to flux, okay, divided by A, right? So we substitute, okay, the given flux, okay, in this question or in these examples, okay, by 800 microweber divided by 0.1, okay, the area is 0.1 meter squared, and will give you, okay, at millitesla or at times with power of times with 10 power of minus 3. Okay, so the flux density, okay, for these examples, okay, give you, okay, and is equal to 8 millitesla. Okay, so for the magnetic circuits, okay, what is magnetic circuits? Okay, so one of the characteristic of the lines of magnetic flux, okay, is that the each line, okay, forms a closed loop, right? So the following, okay, shows the dotted lines represent the flux set up within a ring which made of the steel. Okay, so you have this, okay, this ring which made of the steel, or we call also the toroid. Okay, toroid, okay, because of the, okay, the shape. Okay, so we have the dotted line here, a dotted line here, okay, which present a flux. Okay, the dotted line inside this core, okay, is the flux line. Okay, so the magnetic circuits, okay, okay, one of the characteristic, okay, that have the, okay, the line, okay, the flux line, okay, which is closed loop flux line. Okay, and then the magnetic field also have to complete the closed loop followed by any group of the flux line, okay, referred to as the magnetic circuits. Okay, so this group of the flux line, okay, is referred to the magnetic circuits. Okay, and then magnetic circuits are found in can be found, okay, in motors, generator, transformer, computer disk, okay, computer disk, okay, computer disk drive, and tape recorders, and so on. Okay, so we can find all the magnetic circuits, okay, in this list of, okay, equipment. Okay, so the air gaps, fringing, okay, and laminated cores, okay. Okay, for the magnetic circuit with the air gaps, so this is the air gaps, okay, when we have some division, okay, between this core, okay, you have the air gaps, okay, fringing occurs, causing the decrease in flux density in the gaps. So you have some decrement, okay, in this gap. Okay, the decrement of the flux density. Okay, so for the short gaps, okay, fringing can usually be neglected. Okay, if you have a short gap here, okay, so we can just ignore the fringing effect. Okay, so laminated cores has its effective cross-sectional area. Okay, so can be determined, okay, using the stacking factor. So if you have, okay, this core, if you have the eliminated cores, okay, or you eliminate, okay, this core, okay, so we can consider, okay, the eliminated cores, okay, effective cross-sectional area, okay, which can be determined using the stacking factor. So the stacking factor, okay, is the ratio, okay, or we can determine, okay, by effective area divided by physical area. So the physical area, okay, is the eliminated core area, okay, and then, okay, the effective area, okay, eliminated, okay, cores is also considered as a physical area, okay, and the effective core is the core, okay, that effective, okay, with inside the eliminated cores. Okay, so the effective area divided by the physical area can give you the stacking factor. Okay, so in example, okay, if you have the eliminated section of the core has a cross-sectional dimension of 0.03 meter by 0.05 meter. Okay, so this is the cross-sectional area, and you have the stacking factor of 0.9. So what is the effective area of the core? Okay, and then given flux is equivalent to 1.4 times with 10 minus of minus 3 Weber. Okay, so what is the flux density, or B? Okay, so using, okay, the given formula before, okay, so the effective area of the core is the stacking factor, okay, equivalent to effective area divided by physical area. Thus, okay, the effective area, okay, you rearrange this formula, okay, so you can have the effective area is equivalent to stacking factor times the physical area, okay, which is the stacking factor is given as, okay, 0.9, okay, and the physical area, okay, the cross-sectional dimension, okay, of the core will give you 0.03 times with 0.05, okay, so the multiplication of these two give you the effective area, which is equivalent to 1.35 times 10 power of minus 3 meters squared. Okay, and then the second question, okay, asks you to get your flux density, okay, by using the previous, okay, flux density, which is B is equivalent to flux divided by the area, okay, the unit is Tesla, okay, so you put or you substitute all the, okay, answer that you found, okay, okay, including, okay, the effective area here, okay, as your A, okay, and then with the given flux is 1.4 times 10 power of minus 3 divided by, okay, the effective area here, will give you the flux density B, which equivalent to the 1.04 Tesla. Okay, the next subtopic is about the series and parallel element in magnetic circuits. Okay, so magnetic circuit may have section of different materials. Okay, for example, the circuit in the following figure has section of the cast iron, sheet steel and the air gap. If you see, okay, here, okay, so this, okay, core or the magnetic, okay, the magnetic circuit here has, okay, a cast iron, okay, okay, in this section, okay, and then, okay, this magnetic circuit also have a sheet steel, okay, on this part, and also this magnetic circuit has an air gap. Okay, for these circuits, okay, the flux is the same in all sections. We can assume, okay, using the right-hand rules, okay, the okay, so this is the okay, the direction of current, okay, going in, okay, so the flux, okay, is from north to south, okay, so going up, okay, and then you have the flux is going up here around the series magnetic, around this series magnetic circuits, okay, so you have the, okay, iron sheet different, even though you have the different of the, okay, materials, okay, in these circuits, okay, different materials of these same magnetic circuits, okay, but we can assume that your flux is remain the same because you have a series, okay, series configuration magnetic circuits, okay, right. So a circuit may also have elements in parallel, as shown in the figure. Okay, so at each junction, okay, so you have these two, okay, these two shapes here, right? Okay, so we can consider as a series and parallel circuits. Okay, so a circuit may have the elements in parallel, okay, as shows in the figure below. Okay, so at each junction, okay, the sum of fluxes entering, okay, the flux of, okay, fluxes entering is equal to the flux of, okay, is equal to the summing of leaving. Okay, so if you see here, okay, the current, right, the coil of current at the intermediate leg. Okay, so using the right hand rules to, okay, so the current, okay, the direction of current is in at the intermediate leg, in the middle leg, sorry, okay, and then, okay, the flux is going up here as you compare with the direction of current. Okay, you look at my hand, okay, and then the flux is going up. Okay, so this junction, flux 1, okay, is equivalent, okay, same with your what have you learned, okay, in your circuit theory, okay, the flux or the, if you see, okay, as compared to the circuit theory, this can be considered as the I1, okay, so the I1 is equivalent to I2 plus with I3, same with the flux, okay. So the flux, okay, the summation of this flux 1 is equivalent to, okay, flux 3 plus flux 2. Okay, what is entering to this point is equivalent to what is leaving at this point. What, okay, the flux that leave, okay, at this point is flux 2 and flux 3. So flux 1 is equivalent to flux 2 plus flux 3.